To measure how well artificial intelligence can write code, we typically test these agents inside permissive digital sandboxes. In these standard evaluations, the AI operates as a root user. It enjoys writable file systems and open network egress to pull any dependency it needs from the public internet. But organizations do not deploy code into open voids. Real-world enterprise environments enforce strict access controls, read-only paths, and scoped credentials. To measure this gap, researchers developed Boundary Bench. It evaluates 12 leading coding agents across a nested ladder of security policies mapped to real-world NIST specifications. When you enforce these operating system-level constraints, agent performance degrades sharply. Yet this penalty is distributed in wildly different ways depending on the specific model you deploy. The top dotted line traces the success-to-cost Pareto frontier for models operating in a standard, unrestricted environment. Higher success correlates predictably with a higher token cost. Apply the strictest NIST-derived policy, and the entire frontier collapses. Task success drops, and API costs rise. The penalty is universal, but the currency models pay it in is not. Some models forfeit a massive amount of task success, while others maintain their success rate by absorbing severe token cost inflations. A model's unconstrained leaderboard score does not reflect its operational reality. A top-tier agent in a sandbox may become prohibitively expensive or entirely ineffective the moment it hits a corporate firewall. Boundary Bench does not ask the agent to act securely using system prompts. It enforces the security policy natively at the Linux operating system level. The environment restricts the agent across 3 distinct axes derived from NIST SP 800-53 security controls. First, network egress. Traffic hits a proxy, restricted to a default deny-allow list. Second, file system scope. The agent only accesses a small workspace. The rest is read-only. Third, privilege. The agent is a non-root user. The kernel drops capabilities, preventing escalation. The evaluated agent has no awareness of the benchmark itself. It simply attempts its program tasks and runs into native system errors, like an HTTP 403 denial or a read-only file system rejection. Because these are immutable structural walls, the model cannot bypass them with clever prompt engineering. It must recognize the blockage and construct an alternative system architecture strategy, or it will fail. When we measure how each model reacts to these native walls, the differences are severe. This scatterplot maps each model's shift. The vertical axis is lost success, the horizontal is increased cost. Grok 4.5 sits far right, absorbing 167% cost inflation to preserve success. Conversely, GPT 5.6 Luna sit bottom left, limiting cost but suffering an 18-point collapse in success. The high-cost models preserve their success rate by aggressively brute-forcing alternative toolchains. When a standard package manager is blocked, they route around the blockage, downloading alternative compilers and building dependencies from source. The low-cost models hit the native errors and fail to adapt. They encounter the access denial, cease their operations, and drop the task entirely, rather than spending tokens on elaborate detours. Model choice is no longer an absolute metric of intelligence. The environment dictates the economics, making model selection a strictly policy-dependent decision. For the models that do attempt to maintain their success rates, why exactly does the API cost explode so violently? These agents rarely recognize when a system constraint renders a task impossible. Across the evaluations, the rate of agents stopping early barely shifts under strict enforcement. Instead, they enter a loop of workaround construction. When a repository is blocked, the agent relentlessly rebuilds dependencies from source to create an alternate path. Mapping a task's timeline reveals where passing runs diverge into failure. First is budget exhaustion. Agents grind against proxies until consuming 95% of their time, hitting a hard timeout. Second is flawed workarounds, completing the task in time but submitting an incorrect solution. This massive token burn applies uniformly. Models exhaust API budgets at the same inflated rate, whether they ultimately pass the task or fail it. On specific computer vision tasks, agents struggle to source the necessary datasets through the egress proxy. The median cost for a single run on these assignments triples under strict enforcement. Enterprise hardening converts efficient task successes into grinding failures. You are effectively paying the AI to furiously fight your own firewall. To deploy these models without bleeding budget, engineering teams need a way to predict this operational tax before they activate the agent. The solution is reference solution compatibility. Before running the AI, engineers must analyze if a task's canonical solution relies on actions the policy blocks. We group tasks into affected, where the canonical solution breaks, and unaffected, where it survives. This bar chart compares their mean cost multipliers. On unaffected tasks, cost stays near parity, but on the affected subset, token cost inflates by 2.59x under strict NIST policies. This compatibility check requires zero-agent inference. It can be computed entirely offline, allowing organizations to precisely provision their token budgets in advance. Look back at the success-to-cost Pareto frontier. Focus entirely on this lowest, most degraded dotted line. That represents the final reality of deployed models operating under NIST-derived high enforcement. An unconstrained benchmark score is nothing more than a theoretical maximum. It measures an environment that does not legally or practically exist in enterprise tech. Evaluating artificial intelligence in a vacuum is obsolete. To deploy a coding agent, you must calculate the exact operational tax required for policy compliance.